Now we're going to discuss the Curie temperature from two different points of view. One is the mean field approximation, the other one is the nearest neighbor interaction approximation. So you can recall that in our Langevin theory we had this alpha parameter which is equal to the ratio mh, magnetic moment per atom, times the magnetic field h divided by kBt. Then we said that this H is really the effective field, and we assume that H is equal to the Weiss molecular field. This is the mean field approach, and there is zero applied field. External field is 0. Then alpha must be equal to magnetic moment per atom, Weiss molecular field Hw divided by Boltzmann constant times temperature. And for Weiss molecular field we have gamma times magnetization, gamma times m is the Weiss molecular field, divided by kBt, and we find that the magnetization m is the ratio thermal energy kBt divided by m times Weiss molecular field constant multiplied with alpha. So this was the linear relationship we have observed, and that's the line we draw in m versus alpha plot in comparison to the Langevin theory. And we see that the slope is going to change as the temperature increases. So as T, the temperature increases, we find that the slope dm d alpha is going to increase. And the intersection point with the Langevin function with L of alpha is going to decrease, and when the temperature is equal to the Curie temperature, T is equal to Tc, the intersection point between these two is ms is equal to 0. So therefore at this point so we have the slope of the line that is dm d alpha, which is kt over m gamma, must be equal to the initial slope of the Langevin function. So that is dl d alpha. Now, if you remember, if you go back to the Langevin theory, we have shown that the Langevin function can be expanded into a Taylor series for small alpha as alpha divided by 3, the first term, minus alpha cubed over 45, etc. And we can neglect this one to first order, we can neglect this term, and we can just use alpha over 3 for small alpha values. Therefore, the initial slope will be alpha over 3. So what I would like to do is to have same slopes at t is equal to tc will give us, for dm d alpha, kbtc divided by, so we're looking at dm d alpha, it is kbtc divided by m times gamma. And according to Langevin theory, remember that the magnetization is equal to the number of atoms per volume, magnetic moment per atom, times the Langevin function L of alpha. So if we look at the value of dm d alpha, it's going to be equal to dm d alpha will be equal to n times m times dl d alpha. So we will substitute here nm divided by 3. So this is going to give us, for the Curie temperature Tc is equal to molecular field constant gamma times number of atoms per volume, magnetic moment per atom square, divided by 3 times the Boltzmann constant. If you want to write this in SI, we can basically use mu 0h. So in SI, this has to be mu 0 times n times gamma times m square divided by 3 times Boltzmann temperature, Boltzmann constant. Okay, so remember we talked about magnetization as a function of temperature here. So this is basically what we're doing. We're looking at the slope of this line, m equals hw over gamma from mean field approximation, and equating the slope to the slope of the Langevin function at ms is equal to 0 intersection point when the temperature is equal to the Curie temperature. So that's what we did. Now, if we look at